Hello viewers. In our previous lesson, we understood what we mean by relation from a set A to a set B. We saw that we can associate elements of a set A to another set B if we know how they are connected, how they are related. So, Aparna liked carnation, Vasudha likes rose and carnation, and the third person may like all the three flowers. Now, today's lesson is about when does a relation become a function. A relation becomes a function when every element of the set A is related to, is associated to, is mapped to one and only one element of set B. So, Aparna likes rose, Vasudha likes carnation, Kritika also likes carnation. That is allowed. So, one and only one flower from the set B is related to the person Kritika or Vasudha or Aparna. So, Aparna cannot like two flowers, and such a relation is called a function. At the same time, an element of the set B, for example, in this case the sunflower is not associated with any element of the set A. So, sunflower is not the image of any element coming from set A, that is perfectly fine. And so, what do we mean and how do we define what a function is from set A to set B? Here is the definition. A relation F from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. Now, the words that are highlighted here are every. So, every element of set A must be connected, must be mapped to one and only one image in set B. It cannot be associated with more than one element of set P. With these two conditions satisfied, the relation qualifies to be termed as a function. So, if I have a relation F and a relation G defined on set A has 5 elements 1, 2, 3, 4 and 5, and the two relations are defined as list of ordered pairs, F and G both being given. Now, which of these relations is a function? You also have to give reasons. So, if you keep the definition in mind, all elements of set A must be uniquely related to elements of the set B. So, as you can see in the first case, we are looking at 1, 3, 2, 5, 3, 3, 4, 5, 5, 3. No element in the first position is connected to more than one element in the second. So, as you can see in G, 1, 3 and 1, 5 both belong to G, that is 1 is related to 3 and 5 both, and therefore, G is not a function, whereas F relates every element of a set A to one and only one element of A itself, and therefore, F is a function. We also use the metaphor of a function machine to understand what this abstract concept, which is so basic and important as we progress further in maths, especially when it comes to calculus. Functions is a very, very important basic concept. What we see as a function, as a relation, as a rule, can be understood if you think of it as a machine, function machine, which processes something which is put inside it through the input chute, and it processes, converts it and throws out something which we may call as outputs. So, in this figure you can see some spheres being dropped and the machine processes them and churns out cubes of related sizes. In language of our functions, we can also call these inputs to be the variable x, and the function machine, if it represents say the function f, then it throws out quantities which we write as f of x. These f of x is the output, x is the input. So, if f is a function from set x to set y and x comma y belongs to f, then we also write y to be same as f of x. Read it as f of x, where y is called image of x under f and x is called the pre-image of y under f. Symbolically, we represent this function from set x to set y as f colon x arrow y. So, f is a function from x to y. Instead of words, we use these symbols f colon x arrow y to understand and represent this exact statement. So, remember, x is the input, f of x is the output, y is equal to f of x, y is the image, x is the pre-image. When we collect all these inputs together and make a set, then all of these inputs together as a set are referred to as the domain of the function. Range is the set of all outputs. So, this is also important and significant enough to be remembered. So, keep this metaphor in mind as we investigate and understand this concept of functions further. So, in this arrow diagram, we again have an association represented between elements of set A and set B. So, first of all, does this arrow diagram represent a function? Yes, definitely. You can see that each element of set A has only one image in set B. So, the association can be expressed as f is a function from set A to B, and how is the image coming out? Twice the element in the set A plus 1. So, 2 times 2 plus 1 gives me 5, 2 times 5 plus 1 gives me 11 and so on. So, I can express this relationship in a mathematical form as f is a function from A to B such that f of x is equal to 2x plus 1. So, the set builder form of the relation now is coming out in a slightly different format, and here we are looking at that same association which could be expressed in mathematical language expressing the function present between the set A to set B. The domain of the function f is all the inputs. So, it is a collection which is nothing but the set A, whereas the codomain of f is the entire set B including the 1 and 9 which are not connected with any elements of set A, and the range of f is only the outputs, collection of all the outputs which means 5, 11, 13 and 17. So, range and codomain may not be equal. We saw that earlier as well when we talked about codomain and range of a relation. And do not forget that f is always a relation. So, whatever we had learned earlier stays true even now with an extra condition added in. Before we proceed further, let us also take a look at what we mean by real valued functions and real functions. A function which has either R, that is the set of real number, or one of its subsets as its range is called a real valued function. When the domain of f is also either R or a subset of R, then it is called a real function. Most, in fact, all the functions that we are going to be dealing with are going to be real and real valued functions. In higher classes only, you will be able to understand anything beyond the set of real numbers. But for the time being, all functions are real functions and resulting in real values only. Now, we are moving on to something very interesting. If you remember, we said that Cartesian product which led to relations is a very important concept because it helps us to visualize the mathematical relationship. And when I have collection of points in 2-dimension system, I can always plot them on the Cartesian system, and when they are plotted, they may form a shape, and that shape is what we call as the graph. So, graph of a function are what we are now interested in, and I would like you to think of graph as the faces of functions. If I know graph of a function, you will be able to say many things about it. Let us start with this. Suppose I have a function f from real numbers to real numbers, f of x is 2x plus 1, and I take few of the ordered pairs in this function and I plot them in the Cartesian system. Then it just looks like random points that have been marked. But now if you look closely, this f, the function, is going to have infinitely many ordered pairs in it, because R is the set of real numbers. So, there are infinitely many ordered pairs that are going to be formed, which belongs to R cross R. And if I plot all of them on the Cartesian system, then they are going to trace a locus, a path, which is nothing but a straight line, which you also can accept with an understanding that if y was equal to f of x, then y is equal to 2x plus 1 is a linear equation, and its graph is nothing but a straight line. Now, if I understand this, then from here we will be able to see also that given a graph, am I able to decide that it represents the graph of a function or not? How do we do that? We use something that is called as a vertical line test. The vertical line test says that a relation is a function if there are no vertical lines that intersect the graph at more than one point. Isn't that interesting? Let us try it out. Suppose I have a graph given here and I take vertical lines at different places. If I mark it down in different places, you see that none of these vertical lines are intersecting the graph at more than one point. And the vertical line test therefore says that this graph is therefore representing a function. What about this one? Here I have a circle now. So, is this representing graph of a function? If I take vertical lines at different places, you will see that they are cutting the graph at more than one point, and therefore, this graph does not represent a function. Similarly, if I take another graph, drawing one line is not enough, because in this case, in this position, this red line is not cutting the graph at more than one point. But this must be true for all vertical lines that can be drawn. So, the moment I take another vertical line at a different position, it cuts the graph at not one, but 3 points, and therefore, this graph again does not represent a function of the variable x. So, it may represent a function, but of another independent variable. Well, we will leave that discussion for another time, but this is not a function of the variable x. Let us now familiarize you with some standard special functions. The first one being the identity function. Identity function is defined as a function from real numbers to real numbers, defined as f of x is equal to x. So, every number gets related to itself. When marked on the graph, it turns out to be a straight line. What is the domain of this function? All values that are coming from set of real numbers can be processed by this function, and the output will be the same as what we have entered, and therefore, domain and range are both real numbers. Another interesting function is the constant function, again mapped from real numbers to real numbers. F of x is c. C is a constant that can change. So, I can have c to be -2, I can have it to be 4, or I can even have c to be 0. It turns out to be a straight line parallel to the x axis. What is the domain of such a function? Definitely all the real numbers. I can process all real numbers under this function, and therefore, f is defined as we say for all real numbers. So, the domain is all real numbers, but the range, the output will, no matter what x is, will always be the c, the constant. So, the range is a single element c enclosed in the curly brackets, the set containing c. Another interesting and very useful function is the modulus function. Again defined from r real numbers to real numbers, f x is equal to modulus x. Now, in that case, what we are looking at all the positive values being generated. Before we look at the graph, let us see if I can restate this rule. Modulus x can be restated as x when x is greater than or equal to 0, negative of x when x is less than 0. So, you know that modulus of minus 7 is 7. So, it is negative of negative 7, right. With that in mind, if I plot first part of this function, that is when x is greater than or equal to 0, I get a line again diagonally inclined at 45-degree angle with the x axis. Negative x will be the line in the second quadrant. Put together, the two constitute the graph of f x is equal to modulus x. So, now from the graph, let us see if you can decide what the domain is. Yes, all real numbers, but what about the range? What are the values of the output? Y in this case remains in the along the positive y axis, and therefore, the domain of f is all real numbers, whereas the range is the set starting from 0 including 0 to infinity, all positive real numbers including 0. Another very important function is the signum function, defined as from real numbers to real numbers, f x as 1 when x is greater than 0, 0 when x is equal to 0, minus 1 when x is less than 0. When we plot it, it comes out in 3 parts by the definition. The domain is all real numbers and the range consists of 3 elements minus 1, 0 and 1. Greatest integer function is again one of the very significant and something very unusual here. It is defined to be the value of the greatest integer less than or equal to x. So, if I have to ask you to find what is f of 2 and then f of 2.73, they both take the value 2. Greatest integer less than equal to 2.73 is 2. Similarly, f of minus 1.04, the greatest integer less than minus 1.04 is negative 2, and so on. So, the domain of f is all real numbers, but the range is always, the outputs are always integers, and therefore, the range is set of integers. Graph looks very interesting here. What would you call it? A step like function. It takes the formation of steps, and therefore, the greatest integer function is often read as step like function. Try plotting this now on your own on graph paper and see if you do get exactly what I have here on the screen. I hope you have enjoyed today's lesson and you will stay with us as we investigate more on the functions in our next lesson.